In this video, we're going to take a look at electron arrangement in atoms, better known as the electron configuration, the ways in which these electrons are arranged in various orbitals around the nuclei of atoms. You can do this following three simple rules, and then once you've done this, it'll give a better idea of why atoms react and have the properties that they do. So the first rule which we're going to follow is the Aufbau principle. The Aufbau principle states electrons will occupy orbitals of lowest energy first. That is, the orbitals in the first energy level have less energy than those in the second energy level, all the way up to the seventh energy level. They also will fill in the sublevels from least to greatest. So the s orbital has less energy than the p orbital, which has less energy than the d orbital, which has less energy than the f orbital. So just like humans, electrons are lazy too. They don't want to use more energy if they don't have to. Just like when you get home from school, you want to recline across the couch because that requires the least amount of energy. But if the couch is filled up, then you got to go to the recliner because then that's the next best option for the least amount of energy you need to use. Electrons, again, will do the same thing, fill up from least amount of energy to most amount of energy. The next rule to follow for electrons is the Pauli exclusion principle. It has two different parts. It says that orbitals can hold up to 2 electrons. It also says that if there are 2 electrons in an orbital, in order for them to be able to hang out together in this small area, since they both have a negative charge and they would repel, that they spin in opposite directions to better get along. When we write these electron configurations, we show that opposite spin using an up and down arrow showing that going opposite directions. And the last rule is Hund's rule. Hund's rule states that when I'm filling orbitals of equal energy, each orbital get 1 electron before any orbital has to double up and end up with 2 electrons in it. That way, all the orbitals are spinning the same direction, have all the electrons moving the same way. It's kind of like when you're at a skyrise apartment building and you're waiting for an elevator, and 2 elevators show up at the exact same time, and there's a stranger standing next to you also going up like you are. Well, each of you take your own elevator, as opposed to both of you going into the same elevator and have to share with the stranger. Each take their own. That way, they can be more comfortable and not have to worry about having some weird, awkward conversation about the weather or sports. However, a more common way of looking at electron configurations is rather than do a depiction, it's called the shorthand electron configuration. And you just list out the energy level, sublevel, and then the number of electrons within that energy level, sublevel as an exponent. So here we see 1s2, 2s2, 2p6, 3s2, 3p6, and so on and so forth, all the way through the entire depiction, again, accounting for every electron within that atom. So there are some weird energy exceptions that happen based upon the fact that not only you have energy levels and different amount of energy within those, but the sublevels having different energy too. So the first one is that these d orbitals are actually of higher energy than an s sublevel in the energy level below. And then even crazier, the f orbitals are even more energy than the s and the p in the energy levels above. So you have to kind of account for this as a chart that actually will make this a little bit more easy to follow, which we'll see in a second. But here, kind of get a look at what the depiction of it is. Looking at each s, p, d, and f, we see that as you go from 1s to 2s to 3s, you have energy increasing. Same thing with the p's, the d's, and then the f's if they were all there. And then also as you look across any given energy level, again, 2s to then 2p, p is higher in energy than the s. Looking then at the fourth energy level where this all kind of happens, we see 4s, 4p, 4d, 4f increasing in energy all the way on up the fourth energy level within each of those sublevels. But then you see where the 5s, the 5p, and the 5d all fell relative to those, and you have this weird order that wouldn't quite work the way you'd think, where you just fill the first energy level, the second energy level, and so on and so forth. You actually kind of have to jump between levels at times. So let's kind of put all these rules together and see how we can get an electron configuration. So let's look at the electron configuration of silicon. Silicon, from its location on the periodic table, we find that it has 14 protons, and being an atom that's neutral, it's going to have 14 electrons. So now we have to figure out where those 14 electrons are going to go. And again, going back to Aufbau, we're going to fill them from lowest amount of energy to greatest amount of energy. And for any atom, that first orbital which will get filled is a 1s orbital. It will always have the least amount of energy. Again, not that they're the same between different atoms and different elements, but for each element, for an atom of them, that is going to be the lowest relative amount of energy. Since it's an s sublevel, it has one orbital. We're going to depict that orbital with a box. And then going to Pauli exclusion, we know we can put 2 electrons in that given orbital. And I'm going to put one in there spinning upwards, and then since they're going to put a second one in there, it's going to have a downward spin to again show they're going opposite directions. And now since we've placed 2 electrons, we had 14, again 2 of them are placed, so we only have 12 left. So from there, now we're going to fill into the next lowest energy level and sublevel, which happens to be 2s. And again, even though we're in the second energy level now, it is an s sublevel, so there's only one orbital. And this one orbital can hold 2 electrons. We have 12, so we'll go ahead and put both of them in there, fill it on up. So now that we've placed 2 more electrons, we're down to only 10. And now we can move on to the next lowest energy level and sublevel, which happens to be the 2p. Now we're no longer in S, so there's not just one orbital, but there's 3 different orbitals in the 2p sublevel. And those 3 different orbitals, again, we're going to fill up, but now we get to follow Hund's rule, because we haven't had this situation where we have these orbitals of equal energy. And Hund's rule again says we got to put 1 in each before doubling up. So put 1 in the first one, 1 in the middle one, and then 1 in the last one. And then now that each has 1, we can go ahead and double each of those up. So now we're filled up in the 2p sublevel. And from there, if I had 10 left, I've placed now 6 more. I have 4 electrons in total left to be placed. So now we'll continue on to the next lowest energy level and sublevel, which is a 3s. And again, being in an s sublevel, we have just 1 orbital, and we can put 2 electrons in that 1 orbital. We have 4 left, so we can go ahead and fill that one on up, put 2 electrons in there, leave me with 2 more to go, and then we'll finish off. We'll go out to the 3p sublevel. And again, being a p sublevel, we have 3 orbitals in which we can place those electrons. And here's a situation where we really need to be mindful of Hund's rule, because again, we've got 3 orbitals left, but only 2 electrons left to be placed. So I'm going to put 1 in the first orbital, 1 in the second orbital, and then leave the third one empty, because I only had 2 electrons left to be placed. I can't put them in the same orbital, because not each had 1 yet. Nor can I put 1 in the third orbital, again, because I only had 2 electrons remaining. So I put 1 in the first 2, leave the last one empty, and that is my electron configuration. However, that gets kind of cumbersome to kind of do that over and over and over. So we can use, again, the shorthand notation where I can just take the energy level, sublevel, and number of electrons raised as an exponents. And then you just kind of work your way up from the bottom towards the top, filling it across again till you run out. So 1s2, as we see, least amount of energy, we list that first. 2s2, 2p6, 3s2, 3p2, and there's our electron configuration for silicon. So an easy way to try to remember this weird order in which we fill up all these orbitals is this chart we have here, where you kind of can just list S's, P's, D's, and F's starting from 7 on down. Again, remembering that there are no F's in the third, second, or first energy level, and no D's in the second or first energy level, and no P's in the first, and S again appearing in all. And again, every S sublevel has 1 orbital, and it can take 2 electrons. Every P sublevel has 3 orbitals, and therefore can hold up to 6 electrons. Every D sublevel has 5 orbitals, and can take up to 10 electrons. And every F sublevel has 7 orbitals, and can take up to 14 electrons. And if you just kind of follow the arrows, it gives you the order in which we fill each of those orbitals, again, until we run out of electrons from lowest energy to highest energy, accounting for those weird, funny overlaps between the different energy levels relative to the sublevels and the amount of energy which each one contains. However, what would science be without some weird, funny exemptions? We already had some with those different energy levels and sublevels. We have even more weird ones that kind of go along to make atoms more stable than the way they would end up. We see that orbitals that are filled or half filled are more stable, and again, we'll talk about more down the road when we look at what these atoms, these elements are going to do and why they react the way they do based on these electron configurations. But we kind of already see it a little bit with some of these different atoms and how they will actually break some rules to make themselves more stable. So when doing out electron configurations, if you were to start at 1 hydrogen and work your way all the way up to number 23 vanadium, then you would have no issues at all. But all of a sudden, once you get to 24 chromium, it takes a little turn, a little trickiness, because again, these half-filled orbitals are more stable than partially filled orbitals. So chromium and everybody else in chromium's family actually take an electron from the previous S sublevel to then fill into their D sublevel of that energy level down below and makes them all half-filled. So you have this half-filled S with a half-filled D, which is more stable than having that fill S and then 4 partially filled sublevels within the D sublevel. There isn't a whole lot of energy between that S and the D, so it's better for it to have these half-filled orbitals rather than actually fill in the lowest amount of energy. The same kind of idea happens for copper's family. So copper, as you work your way across again the transition metals in that second to last column of the transition metals, you have 9 electrons filling in for those possible total of 10 in those 5 orbitals of that D sublevel. And so again, it will take an electron from that previous S orbital, pull it up to that D. So you have a half-filled S, which is okay, not great, but again, okay, because it's half-filled. But it will fully fill up that D orbital, and we really like having full orbitals because full orbitals are stable.